Thanks everyone for coming to our talk today. I'm Kathleen Baker. I work at Microsoft on the Edge browser. Right now I'm working on commercial features in the browser. This is my first time at CppCon. I'm very excited to be here. And I'm here with my colleague Chandra.
Hey, I'm Chandra. I'm a colleague of Kathleen, working in the Microsoft Edge browser team. I've been programming in C++ on and off for more than 20 years. This is my first time attending CppCon, so I'm really excited to be here.
All right, just before we get started, note that there are slide numbers on the top right of each slide. So if you have a question, please make note of the number and we'll come back to questions at the end. So motivation for the talk, we work at Microsoft on the Edge browser, which is a Chromium-based C++ project. Based on some frequent code review feedback, Chandra put together a team wiki page, and then we turned that wiki page into this presentation. So it contains guidelines to follow in code reviews. The goal is this can be used as a reference when reviewing code on your own team. And this covers top issues found in PRs on our team. Many of the topics are from the C++ core guidelines or the Chromium C++ guidelines. Some aren't part of either guidelines, but they're still important to consider. And just due to time constraints, these are only the top issues we found. We have more examples in the appendix as well. Also note, even though we're talking about Chromium C++ guidelines, it applies to most other C++ projects as well. So a bit more info about what we work on. As I said, we work on a Chromium-based browser. We use C++20 with no exceptions, and we use Clang. We also work with hundreds of engineers on the same team, so it's really important we follow coding guidelines. As we go through the presentation, each slide will have what's hopefully a slightly fun, cryptic title about giving a clue what the guideline to follow on that slide is. There'll be an example with some bad code, an example with better code, and then the guideline to follow. We'll also be using printf, puts, cout for creating snippets of code. So you can ignore those when following the guidelines in your own code. They're just for making examples. And some guidelines we'll talk about will have compiler warnings or clean tidy checks to use to identify the issue in your code. So we'll be talking about all of these here. So the first topic, scope. So variables on the loose. What does this mean? We have a struct sum class, and it has two member functions and a function foo that returns sum class. Before this if statement, we're creating an instance of sum class. It's not used outside of the if statement. So instead, we can scope the variable to the if statement. Reducing the scope of variables reduces the risk of bugs caused by unintended modification, and it improves readability. It also allows the same variable name to be used after the if-else block. So the title of this slide was variables on loose, and that's because our guideline is to restrict variable scope. Here we have an enum class sum enum, a struct sum class, and function foo that again returns sum class. Here we're creating sum class before this switch statement, but again it's not used after the switch statement. So instead we can initialize s in the switch, and this again restricts the scope of the variable. And we can also do the same for for loops. So you've probably seen the good example of this code in your own code base. So instead of declaring I before the loop, you can declare and initialize I in the for loop. And again, it allows the same variable name to be used later on in the code. Next is enums. Case of the missing case. We have an enum class result, and it has 3 values. We're using the enum in a switch statement here with a default. So this is fine. If we pass in failure 2, it hits the default, returns failure 2, and it works. However, if we add a new value, the switch will now return a wrong value for failure 3. So if we pass in failure 3, it's going to go to the default and return failure 2. So we can remove the default and add a case to handle each value in the switch in the enum. So now we're using all cases in the switch. At the end here, we have a macro to make sure that all cases are used, or all values in the enum are used. So this is not reached Chromium macro. It annotates unreachable code, and if it's hit, it causes a non-exploitable crash and creates a crash dump. So you might have something similar in your own code base as well. So how to know if you're missing an enum value in a switch statement? Here we're missing failure 3. wswitch will detect it if you don't have a default in your switch. And if you do have a default, wswitch enum can be used instead. The type that bit back. We're defining a C-style enum file status, and it has two values, open and closed. We're initializing an instance of file status and implicitly converting it to an int. So this isn't good because it can lead to unintended behavior. There's no type safety here. If we define another enum with the same values, this won't compile. Open and closed are already defined. If we try to forward declare file status in a header, this also won't compile. So to fix all these problems, instead define file status as an enum class, and now you're not allowed to implicitly convert to an int. We can define door status as another enum class, and it can have the same values. So it doesn't have a name clash anymore. And we can also forward declare now. Enum class provides better type safety, prevents name clashes, and allows forward declaration. Here again, we have two C-style enums, and we're trying to compare them. We'll get a warning that this is deprecated since C++20. So it's safer to define it as an enum class instead, and now this won't compile if we try to compare. Next, name drop with style. We have an enum class with a long name and a namespace as well. We're using it in a switch statement, but this is kind of hard to read. There's a lot of words here with the long enum name and the namespace. So instead, before this switch statement, we can use using enum, and this just makes the code cleaner and easier to read. Next topic is iteration. No more index games. We're iterating over a vector of ints using a for loop, using the subscript operator. Then similar here with lists, we're iterating with iterators, or we're iterating using iterators to access the elements. Instead, we can use a range-based for loop. This just makes it easier to read and use. Another way is to use ranges for each. For each is easier if you're trying to apply a function on each item. So for example, if you're printing each item. And then just a little fun fact about how we're using std_ignore here. Using std_ignore out of std_tie is supported by compilers, but it actually was only standardized in C++26. Don't clone what you can borrow. We're iterating over a vector of strings, and we're creating unnecessary copies of each string in the for loop. Instead, we can use const reference or a forwarding reference for vectors of non-trivial objects. We can use the warning range loop construct to flag this issue. Range loop construct is included in WAL. Next, the key to clarity. We're using an iterator to access the key and value in a map using first and second. To improve readability, we can use structured binding with const reference to access the key and value. And I'll pass it off to Chandra.
Thank you, Kathleen. So we'll start this section, which has examples for passing parameters. So our first scenario. Okay, something was wrong with the clicker. Okay, don't clone the elephant for a walk. So let's look at an example. So you have this function print, which takes a string as an argument. And then in the body of the function, it just prints a string. So what can be wrong over here? Okay, I have to keep this clicker in this direction. Okay, so if you look at the body of the function over there, right, we're just reading the string. We're not making copies or not storing it, right? And then we're passing this thing as a by value. A string is not a cheap to copy kind of type. So since we're passing it by value, the copy constructor can get called, and there can be memory allocation. So what should we do in this particular case? A better alternative is to just pass the string by a const reference over here. So which becomes our guideline, that pass non-trivial read-only objects as const reference to prevent unnecessary copies. Now, how can you detect this in your code? So there is a useful client ID check, performance unnecessary value param, which can be used to kind of flag this issue. Now, before moving on to the next slide, just wanted to note this point that the example print actually showed string, but the guidance said pass non-trivial read-only objects and did not mention strings. And the reason is string is special. So we'll see some alternative strategies for string as argument in the later slides. Moving on to the next example. Const without context is just noise. So for that, let's create a simple struct, point with x and y, and then create this function, print point with const point. What can be better over here? So suppose let me drop the const. So the point to note over here is that const here is not part of the function signature. So both these declarations above are exactly the same. If you go and add a pointer and a reference, then those are different. So those are now part of the function signature. So which brings us to this guidance that const is not needed on value parameters in function declarations. So if you have code like this, where in the header you have this print point function which has a const point taken by value, then consider converting to this. Just remove the const over there. Moving on to the next one. Feather is light, let it fly. Okay, let's see some code. So we have a print int which takes an int by a const reference. So as the clue gives it, it's light. So int is a lightweight type, cheap to copy. So there is no need to pass it as a const reference, just pass the value. Similarly, let's look at this particular struct that I saw in the last slide. If you are creating a function like this, where we're passing this as a const reference, this is also not necessary. We can just convert this to pass it by a value. Now, why is it useful to pass this by a value? Because, passing trivial objects by value is preferred because passing by reference can prevent certain optimizations. For example, like if you're passing by value, then that I above and then xy variables inside the point, all those can be passed in registers by the compiler. Okay, so we don't have to dereference memory inside the function itself. Okay, so pass cheap to copy type by value. Next scenario, the final destination deserves a shortcut. So you have a struct A, which has a member variable of string, and then you have a constructor which takes a const string as a reference and then initializes the member variable. We also have a sync string function which takes a const string as a reference and then assigns that to a member variable. So how can this be made better? Well, we can convert that into an R value reference over there. And this comes directly from the CppCon guidelines, which says that for will move from parameters, pass by R value reference, and then stud move the parameter. Keep this in mind. Okay, next scenario. Don't hold the book to read the title. I told you I'll come back to string. So this is the string example. So foo, and then we are passing a const string as a reference, which we are supposed to do, right? That's what it showed a few slides back. So what can be better over here? Okay, so the point to note over here is that, again, this is not making any copies, this is reading it, right? In this particular case, it's better to try and convert that into a string view. So why is it better to convert into a string view? The reason being, the string view can handle more cases. So string view can be called with a string, with a const char star, with a const char star and the length. So we don't need to create different functions for handling each of the scenarios, and also it does not do any kind of heap or memory allocations. Let's look at some code. So what you can see over here is the first one, foo, hello. So that one actually creates a temporary string. The other three calls below, foo better with hello, and foo better with string, and foo better with the pointer and the range. So those don't actually create any string, it just creates a string view over there, so there is no allocation going on. So that's why a single function can handle all these different scenarios. Moving on, look, don't touch the collection. Okay, for this, first of all, we have to introduce a special struct, A. So this is nothing special about this. This is just a placeholder for a non-trivial object that we'll use for most of this presentation. The print statements in the special member functions help us understanding whether they're getting called. For example, like if the copy constructor is getting called, you will see this getting printed. We'll try to see if there can we get move constructor getting called. Even better, okay, can we get an in-place construction? With that said, let's move on to the actual example. We'll just compress our type, and let's look at this piece of code. The foo is taking a const stud vector as a reference, right? Okay, what if we convert this into a stud span? Now, what's the difference? Let's look at some code. So here we have an array of type A with 3 elements, and then first of all, we're calling foo, which calls the vector function, and the other is foo better, calling the span function. Let's look at the output. So as you can see, when we call foo, we have to create a vector, which means that we are creating 3 different objects with copy construction and then having to destroy them. All these are temporaries, not necessary. Foo better creates no temporaries, right? So that's why span is useful. So use span instead of vector or array for read-only containers in non-sync cases to prevent vector creation. Let's look at some more examples of span usage. So this is the same function that we have, and here is us using span with all these possibilities, like we are using it for C-style arrays, vectors, stud array, and also with initializer list. Same function can do multiple things. Before moving on, I just wanted to mention that, okay, this one actually creates extra objects. We have appendix, slides in the appendix to explain this scenario. Okay, next section, returning from functions. First scenario, success with substance. Okay, let's look at some code. So you have the function get name by ID. It returns true when it succeeds, false when it fails, and when it's true, it uses the second parameter that's passed, which is the name, to pass in the string. And here is some code calling that function. So how can this be made better? Okay, for starters, can we actually merge those two types of return value, the Boolean and the string, into a single argument? Of course, we can do that. We can do that with a optional. It's just written for this particular purpose. So we just use a pseudo optional string as a return type. And then, as you can see, the code actually becomes simpler. That particular variable is now constrained to only the scope to the if-else block. So, which brings us to the guideline. Use stored optional as a result type when the function can return bool to indicate success or failure, along with some value only for the success case. Let's move on to the next scenario, a result with a story. Okay, this is a little big function. Let me explain. So, parseInt, it takes a string as an argument, and then it tries to parse it with stoi. If it is able to parse it, it just returns that true, and then sets the second argument, which is value, to the parsed integer. If it is not able to parse it, then it returns false, and then sets the third argument, error, to the error string. And here is some code which calls that parseInt function, and here's some actual code with different arguments. As you can see from the output over here, the first string is 100, which is fine, so we get an output 100. The second string is 100 and some, so it starts with a number, so it again gives a number 100. And the third one has no number, so that's why it fails. There is no conversion. How can this be made better? Okay, we have these three different return types, right? Bool, int, string. Can they be combined together into a single return type? Of course, they can be done. With C++23, we have stored expected. So then the int becomes the success type, the string becomes the failure type, and the code becomes simpler. And as you can see in the block over here, the variable is now scoped to the if-else block only. Which brings us to the guideline. Use stored expected to convert the return types for a function appropriately. Next scenario, premature relocation is costly. For that, we bring back our struct A, and then we have this code. A-foo, we create an object of type A, and then before return, we just call a move. Is this good? Let's look at the output over here. So as you can see, we have a move construction happening. A temporary is getting created, right? What if we go and just remove the move statement from there? Here's the output. So as you can see, in this particular case, there is no temporary. We get an in-place construction over there. So explicit call to stored move defeats the inner view, which is the named return value optimization. Hence the guidance, don't use stored move for such cases. Now note, inner view is not required by standard, but most compilers implement it for such scenarios. So how do you catch such a problem? So there is a flag in Clang, WPS magic move. So when you use that, it actually catches this problem. Okay, next scenario, which is very much related to this, elide the middleman. Let's look at some code. So this is the code that we saw on the last slide, right? Which was supposed to give the correct output. Okay, how can this be made better? What if we remove the name of the type? Okay, we obviously get the same output, but it's definitely better because this is guaranteed copy elision with C++17. Okay, the previous one was inner view, which is like may be done by the compiler, may not be done, but this one is guaranteed by the compiler. Okay, it's also known as deferred temporary materialization or also unmaterialized value passing. Now, so that becomes a guidance that prefer using copy elision instead of depending on inner view. Why this is also important is because named object can cause compilation errors for non-copyable and non-movable types. Copy elision works in both the scenarios. Moving on, next example, a sealed envelope with no reason. For this, we just brought back our construct A and then just updated the constructor to have two integers. Okay? And then we have this code, foo, which returns a const A. Here's this code using foo. So we have a vector, and we're then pushing back foo into the vector, and then creating an object of type A, and then assigning foo to that A, okay? As you can see, foo that's being returned is a temporary, right? And let's look at the output over here. So with a temporary, we expect the move constructor and the move assignment operator to be called, right? But here we are seeing the copy versions getting called. Okay, what if we make a small change and then remove the const over there, right? and then we get what we wanted to get, right? We get the move construction and the move assignment operation. So what is happening over here is that const return defeats move operations. So hence the guidance, don't return const value from functions. So let's dig a little bit more into this one. So if this piece of code, this actually works same both for the const return and the non-const return. Now then the question comes up, why does a developer want to write it that way? Is it just copy pasting code? Is it ignorance, or is it something else? Let's dig into it a little bit more. Let's look at this code. So this one returns a const a, and this code does not compile. So foo is equals to a 1020. This one does not compile, okay? However, if we have the other version which does not return const, this code compiles. And why is this distinction significant in any way? Because POD types behave in this manner. So if you look at integer, it doesn't need to be const, but it behaves in this manner. So if this behavior is important to you, we can achieve that with C++11. We just need to make a minor tweak to the assignment operators. So what we need to do is that we just need to ensure that they are only defined for L value types. So that's where that AND comes into play. And once we do that, we get the parity. Okay, handing it off to Kathleen for the next section.
Thank you. So now we'll talk about class design. First off, init to winit. We have a struct size, and we're initializing member variables in the constructor. Instead, you should initialize them at the point of declaration. This reduces mistakes, missing out on initialization. For example, here, we're not initializing height in the constructor. There's a clean tidy check, CPP core guidelines, protype member init, and this will catch it. Next, list it or risk it. We have a class person, and again, we're initializing in the constructor. Instead, we can initialize in the member initialization list. So this is a style change, but it can also reduce unnecessary calls to the default constructor if it's a non-trivial type. And then another bonus when using the member initialization list, here member A is declared first and member B second, but in the constructor, we're initializing member B as member A plus 1. So member A is not initialized yet. But we don't get a warning, and this compiles fine. So the code is hiding a problem. If we use the member initialization list instead, we can use the warning reorder constructor, and it will point out the issue. So using the member initialization list forces us to ensure the correct initialization order. So we should reorder the list and have member A first. Detached duties. We have a class logger with a public function print hello. It doesn't access any member variables of a class. So we can make print hello static. If member functions don't access non-static member variables or functions, you can make it static. In some cases, it could also be moved out of the class into a namespace if it's not conceptually tied to the class. You can also use the clean tidy check, readability convert member functions to static to point this out. Next, don't crowd the living room. My class has a public member function and a private static member function, calculate result. In the source file, do something called calculate result. However, calculate result doesn't use any of the member variables or functions of the class. We can move the private static function out of the class and into an unnamed namespace. So now the header file will no longer contain the declaration for the function. In the source file, we define the function now in an unnamed namespace. This will reduce dependencies and simplify the header. Next, the redundant ritual. We have a header file here, and we're declaring an extern my function, and we've defined it in the source file. It's better not to declare the function as extern. Extern isn't required, as functions already have external linkage by default, so this is redundant. Immutable intentions. Class point here, we've defined a print function, and it outputs x and y. In main, we're creating an instance of point and calling print. So this works. If we make the instance of point const, though, this no longer compiles. This is because p is const, but the print function is not const. So how to fix this? We'll mark all member functions here const because they are read-only member functions. If the member function isn't modifying any other members, it should be made const. So we can make the instance of point const in main as well. What Clang tidy check to use? There's readability make member function const. It will catch this. So we'll suggest making all three functions here const. Handle with reference. We have another class book. Member function get title returns member variable title, which is a string. Instead, we can return a const string reference to title. Returning non-trivial member variables can be inefficient, so return them as const reference instead. Here's another example returning const reference. We have struct B with a function get A that returns a const reference to member A. Assume A here is the struct that we've seen before that prints when the special member functions are called. We also have a function get B that returns an instance of B. In main, to get a const reference to A, we're calling get B, which returns B, and then calling get A on that. So this compiles fine, but if you look at the output, there's something suspicious going on. So A is destroyed before the log line. If we compile with GCC, it says this is possibly a dangling reference. To fix it, we can overload get A with R value and use move when returning. So you can see in the output now that A is destroyed after the print line. And then I'll pass it back to Chandra.
Thank you, Kathleen. So in this section, we'll consider special functions of a class. Let's start with the first example. Don't panic while moving. So for that, we again have our struct back A, and let's see some code. So in main, we have a vector of type A, and then we are running a for loop with 4 times, and then implicing back I 4 times. Yeah, don't consider result for the moment. It should be done, but that is not specific for this particular example. Okay, so what is wrong over here? Let's look at the output. So as you can see that even in the presence of the move constructor, the copy constructor is getting called during resize. And why is that? The reason being this non-trivial object's move constructor is not Noexcept. So if you just make a minor change over here, just add that Noexcept block over there, this gets the move constructions happening compared to the previous. So consider making move constructor Noexcept. Now suppose we have this case which has a non-Noexcept move constructor. There's a Clang tidy check that can help us flag and find this particular scenario. Moving on to the next example. Don't suppress the essentials. Okay, what can that be? So we have our struct A, and now we create another new struct B, which has only a member variable of a type A. And then we have two user-defined constructors which just both print something. Now, here is some code. We create an object of type B, and then later we do B2 equals to move B. So we're trying to create B2 with a move construction of B, right? Let's look at the output. So as you can see over here, it's calling the copy constructor. So ideally, with a move, we would have wanted the move constructor of A to be called, right? So what is happening? So first, let us try to lose the destructor, okay? And then see the output. So as you can see in this particular case, when we don't have the user-defined destructor, the move construction is happening. So a user-defined non-trivial destructor suppresses the move operations, which brings us to a guidance that, sorry.
I don't know how to.
Okay, fine. Slide 53.
Oops.
Sorry, technical problems.
Yeah.
Oops. Oh, great. Okay, great. Let's come back. Yeah. So guidance is ensure that all special member functions of a class are defined appropriately. So now if we wanted to have our user-defined destructor, what do we need to do? So we need to do more. So we need to at least default all the other special member functions. And once we do that, we get the output that we want. Now, it's a little tricky job to ensure special member functions. So I took this table out of Howard Innan's presentation. It actually gives us all the scenarios. So on the left side, we see what the user declares. And on the top row, we see, okay, what the compiler implicitly declares based on what the user has declared, okay? So in the previous slide, we, the user, declared the destructor. which means it affected these two columns, move constructor and move assignment operator, and then they become not declared, which led us to our predicament, okay? So that's why be very careful to ensure that you are defining all the special member functions of the class appropriately. And this brings us to the core CPP guidelines also. It says that if you can avoid defining any default operations, do so. If you define and or delete any copy, move, or destructor functions, define or delete all of them. And finally, make the default operations consistent. With that said, let's move on to the next topic, which is less is more. Okay, what can that be? We have a struct with 4 different member variables, and we have an equality operator and also a not equality operator, which is implemented using the equality operator. And why do we need that? Because we want to use it in code, and this is the code that we have. Everything's working fine. So what can be better? Okay. We can totally lose the not equal to operator, right? Because in C++20, it is generated from the equality operator, so we don't need that. Is that all we can do? We can do even better. So essentially, we have to notice that in this particular class, right, since all the member variables were being used to do the comparison, we can default it out completely, okay? So this is a good paradigm to follow. Next scenario, the trident of truth. Okay, what can that be? We have a class point, which has equality operator defined and also all the comparison functions, because we want to use them in this way, all the comparison functions being used. This code works just fine. Okay, how can this be made better? With C++20, we have the Spaceship operator, which can help us generate all the other functions. So we don't need to have all this other code. And in this particular case, since all the member variables will be compared, so we can totally use the defaulted version of the Spaceship operator. Okay, moving on to the next scenario, selective trust wins. Okay, let's look at some code. We have a class foo, which has a private member function set secret. Now we want class bar to be able to call that function, so that's why class bar becomes a friend. And which is why class bar can do this, it can call foo set secret. And here is some code in main which does that, and there's the output. Seems good, okay, but what can be the problem? Look at this one. So though we wanted to give class bar access to only that set secret function, because it's friend, so it can access all the private variables, right? So it can do stuff like this, which we definitely don't want. So what can we do to prevent this problem? We have to introduce a different pattern over here. So we introduce this Passkey pattern. What we have done over here is that we have moved the set secret from private to public, and then instead of making bar the friend to foo, we have made bar the friend to the Passkey function, Passkey class. And then the Passkey class becomes the second argument. Now since bar is a friend to Passkey, it can actually call that Passkey to call set secret, but it cannot do anything else. It has no other access. So consider using Passkey pattern instead of making a class friend, because it allows us to ensure very targeted access for only specific class functions. Moving on to the next section, which is move and forward. First scenario, a traveler needs a send-off. We get back our struct A again, and then we have our my class. My class has A as a member variable, and then we have a constructor which takes A as an R value reference, and then just initializes the member variable. And here is some code. So what can be wrong over here? Let's look at the output. So what I see is that we are getting a copy construction. We would have liked the move, right? So what is happening? Let's look at the Clang output over here. It says that R value reference parameter A is never moved from inside the function body. So what do we need to do? We need to call move, okay? And once we do that, we get this output. So the guidance, consider using std move for R values inside functions to take ownership when applicable. If you recall, there was a slide before where I was trying to do converting a const string reference to a R value reference, and there I showed move over there. So this is a similar example over here. Okay, next scenario, pass it as it came. Let's look at some code. Okay, so this is a little daunting code, let me explain. So we have my class again, and we have a string member variable. Now we have 3 different constructors to create strings in different ways. So the first one is a const char reference, const char star, which is creating the string. Second is a const string reference, creating the string with the copy constructor. And the third one is the R value reference to string, creating the string with a move constructor, okay? Now we have another function called create, which is just creates a make unique, just creates a unique pointer out of it. So it gets a variadic number of arguments and passes it to make unique to create that object. Let's look at some code. So here is us creating my class in 4 different ways. So the first one takes a const caster, The second one takes an R value reference. This is a PR value. The third one takes a string reference L value. And the fourth one, again, takes an R value reference. This is an X value because of stored move happening. Here is the output that we see, which we don't want, right? Because this one's, ideally we wanted this one to be called, right? And this was not getting called. This constructor was not getting called, okay? So what do we need to do? So this was the problem. How do you fix it? Very simple. Just go and put the forward over there, okay? Compared to this. And once you do that, you get the proper move construction happening over here. So the guidance is use stored forward when dealing with forwarding references to avoid unnecessary copies. Okay, now let's go back to this code that was not correct. So there is a Clang tidy check, core guidelines missing stored forward. If you use that, it will point out this particular issue. Now let's look at a very related scenario, the next, which is don't drain the well repeatedly. Okay, there's a lot of code, let me explain. So you have a function call all. It takes two arguments. The first argument is a vector of functions. Each of the functions written void and takes a variadic number of arguments. The second argument to call all is a variadic parameter pack. In the body of call all, it runs a for loop on all the functions in the vector, and for each of the functions, just calls that function with the variadic number of arguments with the stored forward. What kind of functions are you using? Here are two examples, func1 and func2. Both of them take a string by value and just bring the string. And here is me setting it up all up. In the main, we're creating a vector of func1 and func2, and then calling call all with funcs, the vector, and then passing the string at the second argument. So what can be wrong over here? Let's look at the output. As you can see, something is wrong, right? The second one is printing empty string. So what is happening over here is that the call to func1 is doing a string move, which is why func2 is printing an empty string, which is incorrect. How do you fix it? Okay, so instead of forward, remove the forward out the way. Okay, and once we do that, we get the correct output. Which becomes a guideline that if you are calling multiple functions using variadic arguments, then consider removing stored forward. Now, obviously, as you can see, this version actually makes copies. Okay, the copies of strings are being made. How do you remove those copies? So you have to write more code, essentially just tag all of them as const reference. And once you do that, your copies are gone. Okay, now let's come back to the bad code, like this, and see. So there is a Clang tidy check, backbone use after move, which can be used to flag this particular scenario. With that, let me hand off to Kathleen for the next section.
Thank you. So now we'll talk about standard template library containers. So first, avoid the detour. We have a struct A defined that has a constructor that takes an int and outputs in each special number function again. We're creating a vector of size 2 and using pushback to add elements to the vector. The output shows the move constructor for A is called, so temporary objects are being created here. We can use the clang tidy check, modernize use Emplace, and this will tell us to use Emplace back instead. So we'll try that out, and now we can see temporary objects are no longer created. So use Emplace back instead of pushback in this case. It also applies to many other containers, like deck, forward list, list, stack, queue, and set. Instead of push or insert, use Emplace instead. And if you're interested in learning more about reducing unnecessary objects, you can come to the talk that my colleague Prithvi and I are giving tomorrow afternoon. Okay, ask the right question. We have a vector, and we're checking if it's empty using size. Instead, we can just call empty. So this is more readable and clearly shows the intent of the code. It also works for other types, and string has length as well. So is there a clang tidy check? We can use readability container size empty. It will give a warning that empty should be used instead. And this also works for other STL classes as well. Next is algorithms. The range revolution. We're trying to sort a vector, and we're using std sort and passing in the begin and end iterators. Instead, we can use std ranges sort. So this is more concise, readable, and reduces the chance of making a mistake. So is there a clang tidy check? You can use modernize use ranges, and it'll say to use the ranges version instead. And these are all the algorithms it can catch, so it's a pretty useful check to use. Erase the drama. We have two functions, remove odd and remove number. We're using erase and std remove, or remove if and remove. The intention is remove odd, removes the oddance, and remove number removes a specific int. Here we're using the code. We have a vector of 5 ints. We're calling remove odd and remove number 2. So we would expect only the value 4 to be remaining. But actually the output is 445. So we have a bug here. What's going wrong? Remove and remove if reorder elements in the vector. So the elements we're keeping are now at the front of the vector. So in remove odd, the even elements are at the front. Remove if returns an iterator to the new end of the vector, and then we're passing that into the vector erase function, and it's removing the element at the iterator passed in. So remove odd is only removing one item after reordering elements. To fix this, there's an overload of erase that takes 2 iterators and removes the elements between, or in the range. So now we're passing in the vector and iterator as well. And now we get the correct output. But an even better way to do this is to use the non-member functions std erase, if, and erase to avoid making this mistake. And there's a clean tidy check you can use. Bug-prone inaccurate erase will point this out. Okay, containment clarity. We have a function that checks if a set contains a value. It's using std find. We have another version using std ranges find, and a third using set find member function. So all of these work, but they're doing the same thing. Instead, we can just use the set contains member function, and this simplifies the code. Contains is present for all associative containers, and it was added in C++23 for some other types as well. And what check can we use? There's readability container contains. It also catches usages of count. So for example, here we're using count to see if set contains 3. We can just use contains instead. Custom isn't always clever. Here we have a function that checks if a span contains an int divisible by 3 and uses a range-based for loop and an if statement. Instead, we can use std ranges any of, and it replaces both the for loop and the if statement. And both actually generate the same code, so it's better to use the existing algorithm here. This example is from Sean Parent's talk in 2013. He simplified some code using existing algorithms. So if you're interested in learning more about this, this is a very interesting talk. And then I'll hand it off to Chandra for the last section.
Okay. Thank you, Kathleen. So move on to a last section, miscellaneous. First example, build where you stand. Okay, let's see. So we have our type A that we created. So now we are creating a std pair A and A in this particular manner. Okay, we are creating an optional of a type A in this manner. We are creating an expected of a type A as a success type in this particular manner. And then we are also creating variant of a type A in this particular manner. And so what is wrong with this one? So let's look at the output. So as you can see, in all these cases, temporaries are being created, right? So how can you remove those? So for PR, we can go and use the piecewise constructor. For optional, we can use make optional, which actually uses the in-place construction of optional. For expected also, there is an in-place constructor we can use. And for variant also, there is an in-place constructor. So here's the output. As you can see, the moment we use those in-place constructors, we get in-place construction without temporaries, which becomes the guidance. Use in-place constructor for various STL types. Moving on to the next example. A unified identity. Okay, there is a lot of code over here, but I've highlighted the important ones. So my class can either represent an integer or it can represent a string. For this purpose, it's storing both of those as separate member variables in optional. It has two constructors, one takes an int, which initializes the int optional, the other takes in string and initializes the string optional. So how can this be made better? Can we use a single type to represent both this? Of course, we can do that. Variant was meant for this particular purpose only. So instead of two optionals, we have just one variant with an integer and a string. So the guidance is avoid juggling multiple variables for type alternatives. Use std variant to unify them under a single type safe container. Though we'll not mention this one, anytime you see an union in your code, right, try to convert that into a variant because it actually improves safety and also maintainability. Moving on to our next scenario, a placeholder, not a pretender. Okay, so I'm creating a visitor because I want to use it with a variant. And then there's a test variant function which just calls visit with the visitor for the variant that is passed in, and here's the actual code. So you have an int man which creates a variant of int and a string, and then calls test variant on it, and then finally changes the type using Emplace from integer to string, and then calls test variant again. And here is the output that you see. So what is wrong over here? If you look at this code, right? So it's using 0 to detect unset state, right? Which is not correct. So what can we do better? We can totally use monostate. So monostate can be the first argument type to denote unset state, and the code also becomes simpler. As you can see, we can detect unset state and it prints correctly, which becomes the guideline. Consider using monostate to represent unset state in a std variant. Now this also comes handy for one other scenario where you have a type which has a no default constructor. So in this case, with the no default constructor, the first code that I commented out, so that will not compile, because that one has the type as the first parameter, a first type, no default constructor, okay? So you have to kind of change it. And then we're creating that variant and later placing the no default constructor into that, and here is the output. First was the string and second was the no default. Monostate comes handy here too, because that is the one that can use to set the unset state, and then the code becomes simple. We can detect unset state, and this is what you do. Okay, if you were worrying about what is that is variant, it's a very small concept that we define to detect variants. One more scenario, don't let it drift. Okay, let's look at this code. So we have a function, simple function with text radius as an argument, and then has a constant pi, and then creates a circumference and calculates an area and then prints those. We have one more function which creates a file path in data and string data and does a lot of dumping out of those, right? Now, if you squint long enough at those functions, you will see that in the second function, once those variables, file path, int data, and string data are initialized, they are not modified again, right? So it may be easier to help explain, right? The moment you actually tag those with const, it becomes easier to understand that code. So consider making local variables which are not modified after initialization const to help with readability and with comprehension. Next scenario, snapshot on arrival. Okay, so here's some code foo. There's a lot of code, but what it's doing is that it's just trying to initialize final value with a lot of conditions. Now the question is that with this present, can you make final value a const? We can do that by using an immediately invoked lambda. So that kind of becomes the guidance that consider using immediately invoked lambda to create const variables when applicable. So most of your cases will not be this convoluted, but many a times we have 2 or 3 different conditions which are used to initialize a variable, and then we create a non-const variable and then keep on adding, assigning to it. So instead, we can use an immediately invoked lambda to get a const out of it. And this will be our final scenario. One definition to rule them all. Okay, we have this, a const expert double in a header. What can be the problem with this? Let's add some extra code. So we had this function get address of pi, which is supposed to get the address of that key pi variable. We have another.cc source file where we define that function, get address of pi, which returns the address of kpi. Now we have another file, main.cc, which has yet another function, print pi address, which prints the address of kpi as main.cc sees it. And then it also calls get address of pi to print the address as another.cc sees it. Let's look at the output. So as you can see, main.cc and another.cc, they see different addresses of the same variable, which is a one definition rule violation. Now this can be very easily fixed. What we can do is that we can just mark that const expert inline. Once we do that, both of them have the same address. So the guideline is add inline keyword to header only definitions to ensure that one definition rule is not violated. Which brings us to the end of our presentation. So some final takeaways. Scope smartly, minimize variable scope in conditionals, loops, and switches to boost clarity and reduce bugs. Iterate elegantly, prefer range-based for loops, structured bindings, const reference, and forwarding references for clean and efficient traversal. Design thoughtfully, use enum class, std variant, std optional, std expected to express intent and avoid ambiguity. Create classes with care. Initialize members early, make functions const or static when appropriate, use idioms like Passkey and Spaceship operator for control and comparison, and always define your special member functions correctly. Modernize with STL, embrace ranges, erase if contains, Emplace style functions, and replace verbose patterns with expressive and standard solutions. And finally, use client ID checks and warnings to help the compiler catch issues for you. Some further resources, many of the scenarios that we have presented, so many more scenarios are also present in the appendix. Many of the code snippets that we presented over here are also present on this GitHub page. I'll show the link later slides also. Now, there are a lot of talks by Microsoft employees at this conference. This was our talk. So there are more talks on Wednesday, Thursday, and Friday, including this talk by Prithvi and Kathleen tomorrow. If these topics interest you, please go ahead and watch these talks. We also have a feedback survey link and a QR code that over there. So if you fill up the survey, we'll have a raffle for prizes as a thank you. And which moves us to the end of our presentation. So on the left-hand side, there's a GitHub link for the code snippets. On the right-hand side, there's a link for the surveys. Questions?
There's a microphone up here.
So how do you handle different levels of C++ knowledge and understanding in your team? Because some of these idioms and solutions you presented, like the immediately invoked lambda, or I was thinking about the defining a variable in like the switch statement. They may not be as readable for people who are new to C++, or even for people who are used to like older style C++. And so maybe like for someone who's more used to like the modern way of doing things, it seems more readable and easier to deal with. But for other people, maybe they see it as more complicated. So how do you deal with this situation?
Yeah, I think that's a great question. So what I'll say is that probably once you see this code a little bit, then it becomes understandable. That's my understanding. So mostly people who come from the C background directly, they actually try to initialize everything at the top of the function, which is not the C++ way of doing things. So what I've seen is that once you tell people to do these things, they seem to be able to do it and have no issues with that. So that's my understanding of that problem and what I've seen. So
Thank you.
thank you. Any other questions?
Hello. I have a series of questions.
Sure.
The first is on slide 31, you talk about returning stood optional instead of stood expected when you're just returning a bool. I was just curious what your philosophy of that was, especially because stood optional doesn't give you the ability to understand why it failed. I'm just curious why you don't opt to use stood expected everywhere.
Right. So this one, right?
Yeah.
So this one actually has only one success type, right? And there is only a bool, true and false, right?
Mm-hmm.
So expected is an overkill.
Gotcha.
Because expected actually the error type can be anything, right? Which can be the except, that's it. Like if you have just have a bool, then optional is good enough.
Gotcha. So if
Makes
it's
sense?
simple enough and there's no reason to have an error code out, then just keep it as an
Exactly.
optional.
So this
Okay.
was actually this case where you're returning bool. So that is the simple case.
My next question is in slide 39, and I want to clarify: is your recommendation that you put you define the variables in the header as well as in the initialization list?
Yeah, I think we do both of those. So
duplicate it.
Yeah. First of all, like if you don't need to define it anymore in the initialization list, don't do it.
Gotcha.
But if you actually, the first guideline is definitely always initialize whenever you actually just declare the variable, if you can.
That makes sense. And then my last slide is on slide 42. It's about moving functions to an anonymous namespace. I'm just curious about how you go about testing when you move those functions to an anonymous namespace.
Right. So if you look at this one, right, this is a private function. So essentially the private function can only be used by this class.
Right.
Right. So it means that unless there is any other thing that's a friend, there's nothing more to test.
Right. Okay. Thank you.
Any more questions? Sure.
Yeah, great presentation. Thank you so much. So you had mentioned a number of Clang tidy flags to add. So just curious what your take was on, or what your process was for which ones to add, if there's an easy, like just tidy everything. I want to know everything about my source code, or what tools you use to kind of manage that. Because it just seems tedious to like when you should be applying Clang tidy and which ones you should pick and all that.
Right, and I think that's a good question. So for us, we do have a list of Clang tidy checks that we run. Some of these are actually part of that list. Okay, for example, like there are some tests that we use for security, and they actually start with bug prone. So those are the ones we use. You are always welcome to kind of run with all Clang tidy. It just takes a long time to kind of run, a little more time to run. So I cannot give you a good guidance. Maybe just try it out in your code base and see whatever works.
I was afraid of that answer.
Because some of them actually are not that great. So one of the things you can do is that there are some with CPP core guidelines, which you can definitely use. There are some with modernize, which you can definitely use.
Okay.
And there are a few others like bug prone ones that you can definitely use. The others you have to just pick and choose.
Yeah, got it. Cool. Thank you.
Thank you. Any other questions? Okay then, thank you all.
Thank you.